Okay, number 2 video for using data to approximate a continuous random variable, and we have the same learning goals as last video. Make sure you watch that one, and remember, continuous random variable is one that can take any real number value within a certain interval. Okay, so continuing on here, if we have let's say we have variable w, might be the weight or the mass or something, right? Not that those two things are the same, but whatever it is, if we have that, w is a continuous variable, it cannot take on an exact value. It can't take on one specific value in these, because there's an infinite number of values that can occur within an interval. And so the probability of an individual value is 0. So what I'll show you now is what we do when we're estimating probabilities within a certain interval, how we deal with this. So we see our histogram there, and we can see that we have rectangles, of course, in each of these from each of these intervals in the histogram. Okay, and that's what gets us out of this situation above, where we have this 0 of an individual amount. We use an estimation. Now, it all depends on what level of precision we're working at. Okay, so 83, okay, as an integer, okay, a whole number, positive integer, would be set up like that, between 82.5 and 83.5. Notice how the first inequality is inclusive and the second one is exclusive. Otherwise, you're going to have double ups. If you think that through to the next interval and the interval after it, we're going to have issues with things like 83.5 if it's not exclusive on this one, because it will start at 83.5 at this end on the next one, and that'll be inclusive. Okay, if you go to another decimal place, you need to go to that extra decimal place with the intervals, and so on and so on. So for the probability that a weight or a mass equals 83 exactly, what we do is look at the probability that it's in that interval there, and we have the shaded area divided by the total area, so it's still relative. And in the last part of the video, I'll show you an example of this. Now, we're using this this method as an estimation, as I've been saying, and that can vary too. The estimation can improve. Like, suppose we have a larger sample size and the class intervals were smaller and smaller, okay, and you had smaller and smaller columns and more, and they all had their own little heights, okay, and then eventually you could get a polygon, which, remember, polygon is a sort of a straight line graph that connects the midpoints of each of the histogram columns. As the columns get greater in number, and as they get narrower and narrower, this curve will approximate a smooth curve, and we'll have an area underneath. And that's where we're heading, not so much in this video, but certainly as we move from this one into the next one. And so we eventually can use integration, not in this video, in the next one, because we have basically a situation just like the fundamental theorem of calculus, the first fundamental theorem, where it's the limit of a sum. So that's coming up. So the quality of estimations or the precision of estimations can vary depending on how many columns and, of course, the width of each column. So whether it's an estimate or it's a smooth curve, the absolute area bounded by the curve and the x-axis can have any value greater than 0. What we do is standardize it, so we scale it down so that the total area under the curve is equal to 1 unit, and that's referred to as a probability density curve, or a PDF. Okay, and that's where we're heading. We're going from estimations in this video, and next video we're talking about the probability density curve, the PDF, and of course this is always for continuous random variables. Okay, so this is the last part of the video, and I said I'd do this. Basically, we're using methods that are a bit like discrete to approximate continuous, okay? And next video we'll actually go to the probability density curve, which is continuous in nature. Right, here's an estimate-based example. In a study of nose lengths, okay, Pinocchio, we've got the variable x, we're talking millimeters, and we have a sample size of 75 adults. So that's the data we've collected. The results of the study, here's the data as shown below. So because we're looking at whole number quantities is how we're going to report this in. You can see that the interval is set up to 1 decimal place, and with a whole number in the middle, it's appropriate to have 0.5 on either side. But just remember, one of them has to be exclusive and one of them has to be inclusive. Okay. Alright, this one's different to the other examples. It's got the exclusive one first and the inclusive one second, so that can happen. Alright, as long as it's not both inclusive or both exclusive. So you can see the frequency data and the intervals there. Determine the probability of someone in the study having a nose length that is between 42.5 millimeters and 47.5. Whether you read it off the graph or straight out of the table, it's probably easier to read it straight out of the table. We're looking at that there, so we have a frequency of 21. So the corresponding column goes up to 21. So we're going to use that 21. So we have a frequency of 21. That's how we write it there. And then we know that the sum of all the frequencies is 75. Even if we weren't given that in the question, we could sum all of those frequencies together for the entire set. Okay, so the probability that, now I'm making an assumption here that it says between that. That's why I've set mine up like, my inequalities up like that, okay, to match the table. But I guess it's possible that someone might have meant exclusive, and you know what, the answer would be exactly the same. Alright, because the probability of being exactly 47.5 is 0, so it makes no difference. But I like to write it like that. That way there's no assumptions that we're going into there in any way. So yeah, so we've got 42.5 less than x, which is less than 47.5. That equals frequency. It's a little bit of notation to write if you want to do full justification. So it's the relative frequency. Okay. Okay, so on the bottom I'm going to put, on the top I'm going to put 21, on the bottom I'm going to put 75, and that's 0.28. So the probability that somebody is between 42.5 mil and 47.5 mil in nose length, okay, is 0.28 according to the data from that study. So the probability now in part B of someone having a nose less than or equal to 47.5 millimeters in length. So we've got probability, we have x is less than or equal to 47.5, and so we have the frequency over the total of all the frequencies, which is the relative frequency, and again that's 75. Okay, let's determine the frequency for less than or equal to 47.5. So there's 47.5 there. So we've got these 2, 3, 4 columns here. So it's actually easy just to count it off here. So 2 and 5 is 7, 17, and 7 is 34. And we've got one more, 34, 54, 50. Sorry, I miscounted that. Start again. 2 and 5, 7, 7 and 17 is 24. 45, that is. My apologies. And that's 0.6. such a person would have a probability of 0.6 according to the data from that SAR study for their nose length.